Hello everyone, we're going to be going over section 8.2, which is on the law of sides. We have three objectives in this section. So one, we want to solve SAA or ASA triangles. It stands for side, angle, angle, or angle, side, angle triangles. Two, we want to solve for side, side, angle triangles, or SSA triangles. And three, we want to just solve applied problems. So before we jump right into it here, we want to go over some new terminology for triangles. So if none of the angles of a triangle is a right triangle, then the triangle is called oblique. So this means that if we don't have a single right angle, so this means that all of our angles are going to be less than or greater than 90 degrees. So an oblique triangle will either have three acute angles, so three angles that are less than 90 degrees, or two acute angles and one obtuse angle. And an obtuse angle is an angle that measures between 90 degrees and 180 degrees. So this is going to be one very large angle or very wide angle and two very small acute angles. Or you can have an oblique triangle that is just three different acute angles. So if we look at our image here, on our right, we have our two acute angles and one obtuse angle. Our obtuse angle is our wide angle here. These would be our acute angles here at each end. Then on our left, if we have all angles are acute, we have this triangle here. It's a little lopsided, a little funky, but we see the sides correspond to certain angles. So we see that angle capital B corresponds to side lowercase b, angle A corresponds to lowercase side a, and angle capital C corresponds to side lowercase c. So when before we had our lowercase c indicating our hypotenuse, that corresponded to our 90-degree angle. Now we don't have a hypotenuse anymore, so our angle C corresponds to our length, lowercase c. So to solve an oblique triangle means to find the lengths of its side and measures of its angles. So same as before to solve a right triangle. We're still just finding lengths of sides and measures of angles. But to do this, in the case of oblique triangles, we need to know these four different cases. So case one, we have one side and two angles are known. So this is angle, side, angle, or side, angle, angle. So looking at our triangles below, case one is angle, side, angle, and side, angle, angle. So this means that we're given one side with two angles. So each angle that corresponds to basically essentially the two corners of that side. Or with side, angle, angle, this would be you have one length of your side and one angle is given in one of the corners, and then you have the opposite angle. So that would be side angle, angle versus angle, side angle. In computing them, there really is no difference in the computation. It's really just how they're set up differently. Then for case two, we have our side, side angle. So this is two sides and the angle opposite one of them are known. So this is a whole length of our side according with another side and the angle that is then opposite. Let's find that. So this would be, this angle here is known and corresponds to our opposite side. Then we have case three, which is SAS, which is side, angle, side. So two sides and the included angle are known. So we would know both sides in this case. Two sides and the angle, these would all be known. And then lastly, our case four here, which is just side, side, side. So this is all three sides are known, but no angles. So these are the different kinds of oblique triangles and how we would go about solving for their sides and angles. So the law of sines is going to be used to solve triangles for which case 1 or 2 hold. So our law of sines corresponds to these cases here. Cases 3 and 4 are going to be considered when we get to the law of cosines, which is in the next section. So cases 3 and 4, this is law of cosines. So we'll get to those a bit later. So our theorem here for the law of sines, we say that for a triangle with sides A, B, C, and opposite angles capital A, B, and C, respectively, is going to be that sine of capital A divided by lowercase a is equal to sine of capital B divided by lowercase b, and sine of capital C is equal to lowercase b. Sorry, C. Oof, man, all those different letters get them all mixed up. So we're stating that each one of these values are going to be equal to each other. From saying this, we also get these equalities. That sine of capital A divided by A is equal to sine of capital B divided by B. Sine of capital A divided by A is equal to sine of capital C divided by C. And sine of capital B divided by B is equal to sine of capital C divided by C. So we get these three different equalities stemming from the one single kind of three-way equality that we got from our theorem of the law of sines. So typically to solve triangles with the law of sines, we want to use the fact that the sum of the angles of any triangle is going to equal 180 degrees. So this would be your three angle measurements, capital A plus capital B plus capital C, is going to equal 180 degrees always. Since triangles have measures of 180 degrees, this means that the three angle measurements inside of your triangle have to equal 180 degrees at all times. So all right, objective 1, solving an SAA or ASA triangle. So for example 1, we want to solve the triangle A is equal to 40 degrees, B is equal to 60 degrees, and lowercase a is equal to 4. So the case here with we have of this problem, we see that we are given two angle measurements and our side here. So we're given one side, we have one angle measurement that is connected, and then we have the angle measurement that is opposite. This means that we're dealing with a side angle triangle. So we can just say this is a side angle triangle. So we'll state that right off the bat. So we know this is a side angle triangle. We know we want to find all the lengths of our angles and our sides. We have two angles, so we want to find that last angle. So let's find the value of capital C first. We know that A plus B plus C is equal to 180 degrees, where we have that A is 40 degrees, B is 60 degrees, plus C, which is equal to 180 degrees, which means that C is 80 degrees. So now we have our value of C. So all of our angle measurements are now accounted for. So we can say we found all angle measurements. Now we want the side values. So now we're looking for lowercase c and lowercase b, since we saw that uppercase C was 80 degrees. So we can use the law of sines to find the values of C and B. Since we have all of our angle measurements and we already know what the value of lowercase a is going to be, we can use this twice. In this case, we're going to use two separate equalities. We can use this to go ahead and solve for our lengths of C and B. So first we can say that sine capital A divided by lowercase a is going to be equal to sine of capital B divided by lowercase b. And sine of A divided by lowercase a is equal to sine of capital C divided by C. Then filling in the values that we already know, we can get that sine of 40 degrees divided by 4 is equal to sine of 60 degrees divided by our value of b, which we don't know yet. And we also get that sine of, once again, 40 degrees divided by 4 is equal to sine of 80 degrees divided by c. So we're using our law of sines in order to try and solve for specific values. We can rearrange each one of these equalities so that we are solving specifically for the measurement that we want. So on our left-hand side, we can solve for b, and if we solve for b, we end up getting this value here of 4 times sine of 60 degrees divided by sine of 40 degrees. And this is just if you rearrange your equality to now solve for b. Then if you want to do the same thing with c, you would then get c is equal to 4 sine of 80 degrees divided by sine of 40 degrees. And just as before in our last section, we want to use a calculator. These are now problems that we can go ahead and solve using either unit circle or our brains. So we want to go ahead and use a calculator. So if we plug in this value for b of 4 times sine of 60 degrees divided by sine of 40 degrees, this is going to end up giving us a value of 5.39. And then our value of c here, where we calculated 4 times sine of 80 degrees divided by sine of 40 degrees, this is going to give us a value of about 6.13. So that gives us our final values. The values that we were looking for, according to this equation, when we wanted to solve our triangle, we were looking for the values of capital C, our angle measurement, and lowercase b and c, those side lengths. So you can say thus, angle C is equal to 80 degrees, side B is equal to 5.39, and lowercase c is equal to 6.130. And those would just be the missing values of our triangle. So when you go to use the law of sines and you use sine of capital A divided by lowercase a is equal to sine of capital B divided by lowercase b, anything along those lines, whenever you have those equalities, if you have a whole number value, it is best to use that value. Even though we could have gone in order instead of doing them at the same time, we could have solved for the value of lowercase b maybe first, and then solved for the value of lowercase c. And we could have used the value for lowercase b, but as we saw, it ended up being a decimal value. It was 5.39. And when we found this decimal value, we round to the nearest, we rounded to 2 decimal places. And because we rounded, if we use this value in our calculation for the law of sines, it would just make our final value a little bit more inaccurate. And not to say that you wouldn't get the wrong answer, it just makes it much more likely that you would end up with a wrong answer considering that we rounded that value. So if you ever are given a whole value and it is applicable and you can use it, it's better to just use that multiple times than trying to use a decimal value other times as well, because then that would just increase your chances of actually having the value wrong. So all right, let's move on to our next problem. All right, we want to solve the triangle A is equal to 30 degrees, B is equal to 20 degrees, and C is equal to 5. So in our last problem, we saw that we had 3 acute angles. So that was the example of an oblique triangle using 3 acute angles. And here we see we're most likely going to have an oblique triangle that uses an obtuse angle and 2 acute angles. Well, let's just go ahead and look at our triangle first. So we have this length 5, and we were given our 2 angles that correspond to the 2 corners of our length 5. This indicates that we have an angle side angle triangle. So this is an angle side angle triangle. As far as computation goes, we're going to do the exact same thing that we did in our last problem, just identifying the difference, could end up being a question on some homework, quiz, or exam. So we've identified this as an angle side angle triangle. We have the values of A and B, so we can go ahead and find the value of C. So we know that C can be found by stating that A plus B plus C is equal to 180 degrees, where our values of A is 30 degrees, B is 20 degrees, plus C, this is all equal to 180 degrees, where 30 plus 20 is 50, so we have 50 degrees plus C is equal to 180 degrees, which really just gives us that C is equal to 130 degrees. So our angle measurement, C is equal to 130 degrees. This is our obtuse angle. It's between the values 90 and 180. So we have our obtuse angle, but this is our value of C here. So now this angle C, this is 130 degrees. And now what we need to find are our side lengths A and B. And we're going to do the same thing as we did in our last problem. We're going to use the law of sines to find the values of A and B. So using our law of sines, we know the angle measurement, capital C, and we know the side length, lowercase c. So we're going to use these values and equate them to sine of capital A divided by lowercase a and sine of B sine of capital B divided by lowercase b to find the side lengths A and B. So let's go ahead and first state sine of capital C divided by lowercase c is equal to sine of capital A divided by lowercase a, and sine of capital C divided by lowercase c is equal to sine of capital B divided by lowercase b. Plugging our values in, we get sine of 130 degrees divided by 5 is equal to sine of A, which was 30 degrees, divided by lowercase a. Then once again, we have sine of 130 degrees divided by 5 is equal to sine of 20 degrees divided by lowercase b. So once again, we want to go ahead and rewrite these equalities so that we're solving specifically for the values of A and B. Solving specifically for A, we're going to get A is equal to 5 sine of 30 degrees divided by sine of 130 degrees. And when we solve for B, this is going to be equal to 5 times sine of 20 degrees divided by sine of 130 degrees. Plugging these equations into our calculators, we end up getting for the value of A, which was 5 times sine of 30 degrees divided by sine of 130 degrees, was equal to about 3.26, while the value of B, which was 5 times sine of 20 degrees divided by sine of 130 degrees, came out to about 2.23. So these are the missing values that we wanted along with the value of uppercase C. So in our final statement, we can say thus C is equal to 130 degrees, A was equal to 3.26, and B is equal to 2.23. And these there were our final answers. So once again here, we saw that since we knew the values of capital C and lowercase c, and they were both whole numbers or whole degree measures, we just used that twice. We didn't use our decimals because that would just make our answer more likely to be incorrect. So once again, we did see that we just used it twice instead of using the value that we had just recently solved for. So all right, objective 2, we want to solve for side-side angle triangles. So case 2 is referred to as the ambiguous case because the known information may result in one triangle, two triangles, or no triangle at all. So a bit confusing. Let's look at this picture that we wrote in earlier. It's up here somewhere. Here we go. Case 2 for our side-side angle. So this ambiguous case of using our two sides and the angle that is opposite one of them is known. So using this case, we can state that we can actually find either one triangle, two triangles, or no triangle at all. So a bit confusing and a little troublesome to decide when and kind of where you'll end up with as many triangles. So the key in this case to determining how many triangles, if any, can be formed from the given information lies primarily with the relative size of A, the height h, and the fact that h is equal to b times sine of A. So let's break this down a little bit more. If there's no triangle, so when you're solving this problem, if there's going to be actually no triangle, if A, lowercase a, is less than h, the height, which is equal to b times sine of A, then the side A is not long enough to actually form a triangle. So we see here in our image that A, lowercase a, is actually less than the height. This would mean that we didn't actually form any triangle, so therefore there is no triangle. So once you've found this out about any problem, you just immediately say, oh, okay, well, there is no triangle. Then if there is one right angle, this would mean that A was equal to h, which was then equal to b times sine of A. Then we say that the side A is just long enough to form one right triangle. So because it perfectly matched the height, this meant that it perfectly created a right triangle. Then for another case of one triangle, so this case not a right triangle, but just one triangle, if lowercase a is greater than or equal to b, only one triangle can then be formed. But then the other part here for the two triangles is that if h is equal to b times sine of capital A, if this value is going to be less than lowercase a, and A is less than lowercase b, then the two distinct triangles can be formed from the given information. So we see here are two values of A, where one is going to be greater than h equals to b times sine of capital A, and then this A in the middle here that is then less than our side angle B. Then for our one triangle, we're stating that if this length A was greater than or equal to this length B, then we only have one triangle to deal with anyways. All right, so a bit confusing there. It's really just going to take practice in recognizing what you have in problems, what you do not have, in order to really tell the difference here. Fortunately, the law of sines leads us to the correct determination, and we do not need to rely on a figure or a complicated relationship. So we don't have to rely on pictures like this to really determine the answer. If we just go ahead and start using the law of sines, it will lead us to the correct determination. And as we work through our next few problems, we're really going to see how this ends up working.